before we actually get to the notes for you to fill in, let's just look at a few things. These are some common objects that are shown as viewed under the microscope. So see if you could guess. Raise your hand if you want to take a guess. What is this? Chat?
A bug wing?
A what?
A bug wing?
Okay, good guess. Danielle?
Dried up syrup.
It's actually a CD or DVD. These are the sort of bands that store the
Are you sure
information.
they're not Fruity Pebbles? What?
So, anyone want to take a guess? Devin?
A stick?
No?
What?
Wyatt?
Is it even zoomed in?
Is it like stuff under your desk?
No? These are razor blades, and these are somebody's like beard hairs.
Oh my god! No. It zooms in that much. Stop.
Oh, rocks.
You are correct in a way, Danielle. Faith? No, but you're getting closer.
Is it mineral?
It is salt and pepper. It's magnified. That's what it actually looks like. How about this? This should be an easy one. Raise your hand.
Oh my god, I really don't know.
I forgot what it's called.
Maddox? Yes. Velcro. Do you know the generic name for, so Velcro is like a brand name?
Oh, really?
Do you know the generic name for it?
Sticky.
Hook and loop fastener.
That's stupid.
The way that Velcro works, the like scratchy side is this side. It's made of thousands of little plastic hooks that are flexible. And then the soft side is just this wound up thread material. And when you push it together, the hooks grab onto those loops of the thread. And when you pull it, they sort of can stretch out, they're flexible, and the loops detach. And you can open and close it.
Wait, does it have like the red and blue blades? So like, you know how you said that it makes it red and blue on each side? Like the...
Oh, no, that's just colored that way.
Oh.
All right, here's one.
Oh, wait.
Wyatt?
Skin.
No? Toilet paper.
That's skin?
That's
Oh, Kaylin. Thanks for putting that mental image in our head.
It's like the...
This one, I don't know that you probably have heard of this, but this is a material
Oh, is it paracord?
wound up. These are from nylon stockings. You know what stockings are that like wear on your legs? That's the nylon fiber that's in there. All right, real quickly, I'm just going to show you these. It's under a microscope, Sage. This is a pen, a ballpoint. This is the roly part. This is the ink is back behind there. It's again in a microscope. It's something small. It's not the Grand Canyon. It is the grooves in a record, which as the needle moves through them, plays a sound.
Breadstick. Pocky.
It is a small object, students. It is a toothbrush.
Toothbrush is shaped like that. Seaweed.
All right, let me do my mindful breathing for a second.
It's a cat.
It is eyelashes. That's makeup on them.
It's chopsticks. It's chopsticks.
Dental floss. Tooth plaque and gunk from in between some of the teeth. All right, so we are going to continue on here.
That was disgusting.
So let's talk about how we use the microscope and some details about it. So we call, just like, what do you call a word that has two parts put together, like doghouse? A compound word means it has two parts. We call this a compound microscope because there are two separate lenses that actually magnify the image. There's the eyepiece lens that you actually put your eye up to, But then there's also the objective lens, which you can rotate and select through. So that's why it's called a compound microscope. So can you guess, if I want to know the total magnification of this microscope, anyone want to venture a guess as to how would I calculate it? What?
You see how much it magnifies,
Okay.
and then you times it by that number.
Okay, good. Yeah, you multiply. So this lens that I have selected here multiplies the image 4 times bigger. But then when that image gets to the 10x eyepiece, that takes that large image and magnifies that 10 times bigger. So we have to multiply the power of the eyepiece times the power of whatever objective lens we have. So if I had a 10x eyepiece connected to a 30x objective lens, the total magnification of that would be
40.
Or
300. We multiply eyepiece times objective lens. So what that means is what I see in the microscope is 300 times bigger than the actual size that it is. They are expensive when we carry them around, carry them with 2 hands, one hand underneath the base, one hand on the arm, so that they don't fall. Put them down gently, don't bang them around, because if they get out of alignment, it makes it really difficult to see anything. Magnification.
Are we gonna label? Top?
Yeah.
Wait, I didn't know it was written down. Go
We'll
back.
copy it over from Jake. All right. Now, this is really important, because if you do not follow the steps to find something in the microscope, it's really difficult. But if you do follow the steps, it's actually really easy to find your object, to focus it, and to see it at different magnifications. So I'm going to tell you about this now, and then you'll be able to practice it, hopefully, today. So first of all, we always start on the lowest power. On our microscopes, it's the 4x objective. It's the shortest one. On these microscopes, it has a red ring around it. Okay. You place whatever slide, so we look at objects that are on the slide, or we make our own slides. We put our slide on the stage, we can clip it down, turn on our light, we have our low power objective selected. Okay, so our slide is on the stage. You could see where the light's shining through. So you're going to put the specimen you're looking at over that light. And then you're going to look through the microscope. And what you'll see is a circle. You'll see a little, it looks like a needle in there. It's called a pointer. Okay? And you'll look in there, and at first you might not see anything. To see the object, you'll have to focus it. So on low power, you're going to use the large coarse adjustment knob. So you could move it towards you, and like this is just coming to focus. I see some circles on here. So now it's in focus, but the object I'm looking at is not in the middle of the circle I'm seeing. So we always want to make sure we center the object. And we want to make sure the focus is excellent, very crisp and clear. Just like this, we have it. So if we want to then magnify the image even more, okay, we're going to switch to medium power. But before we do that, we make sure that the thing we want to focus in on is right in the middle of the field of view. Okay, so here this little creature is in the middle. So when it zooms in on the center. So if this were off to the side, and I switch power, it wouldn't be in the field of view because I'm zooming in the middle. So we make sure it's in the middle. Then we could rotate to the medium power, the 10x objective lens. So once you've done that, the object should still be in focus. If you did it correctly, it should be in focus. Now it might need a little bit of adjustment. So you could, again, turn the coarse adjustment a little bit. As you go up in power, you need to move it less and less. So just a small movement will focus on the object. Okay? If you want to then see it under high power, it's the same procedure. You center the specimen so you can see it clearly. You make sure it's focused. And then you switch to the high power objective. Now, often things are more difficult to find under high power. If you look at this, look how close the objective is to the slide. It's almost touching. So when we switch to high power, to focus it, we need to barely move this objective lens. So we no longer use this large coarse adjustment knob. We use this one, the fine adjustment. That's how we focus under high power. It will move the objective small amounts so that you can get it in focus without getting it out. Once you have it there, you'll see it under high power. So those are our steps. Now sometimes you'll get to high power and you can't see it. When that happens, you just go back to medium or low power and sort of start again. Find the specimen, focus it, center it, and then move up in power. Okay? But if you don't see it under low or medium power, you're not going to get it under high power. So don't just like switch, say, well, I don't see it in low, maybe I'll see it in medium. You won't. If you can't see it in low power, you won't see it in medium. If you don't see it in medium, you won't find it in high power. Right, so like this would be it under 40 times magnification, 100, and 400. Now, some people try to keep both eyes open. You can do it. If you look with your dominant eye, it's a little bit different. It's really not a big problem for us. When you use a microscope for a long time, hours, it's kind of straining on your eye to always keep one shut. But if you practice, you might be able to keep both eyes open. It might be easier on your eyes. Typically, you'll take off your glasses too when you're using the microscope. But you don't have to. You can see however it works out best. So what we talk about when we're using the microscope is the field of view. The field of view is that circle that you see when you're looking through the eyepiece. And the field of view gets smaller as we zoom in on your object. You know, if you think about it this way, if I'm looking across the room, I could see the whole wall. What if I added some magnification and used binoculars? Would I be able to see the whole wall?
No.
No, I'd see a more narrow field of view. Then I switch to a telescope. What would happen? Again, I'd see a more narrow, smaller area. Now what I see is going to be larger, but I'm seeing a smaller and smaller area as I increase my magnification. So under 40x, we might see a wide area. Under 100x total magnification, we see smaller. And under 400, we see a much smaller view of our specimen. Here's an example. This is a field of view. This is a paramecium we're seeing in the middle. It's a single-celled living organism. So red is what I would see under low power. I could see all of it. If I were to switch this microscope to medium power and zoom in on the middle, I would see less. And if I switch to high power, I would see even less. So as your magnification increases, your field of view decreases. All right, I can go through this quickly. So if on our microscopes, our objective lenses are 4x, 10x, and 40x. Low, medium, and high power. So what in our eyepieces are all 10x. So what are my possible magnifications? If I have the low power objective lens set, what's my total amount of magnification, Jackie?
40?
Yeah, it would be 40x. What I'm seeing would be 40 times larger than actual size. And if I switch to medium power, Wyatt?
100.
Be 100x. And if I switch to high power, Sophia?
400.
It would be 400x. Which of these gives you the largest field of view? Jake in the back?
40x.
Yes, the 40x. The low power gives you a wide field of view. High power gives you a smaller field of view. So the higher your magnification, the smaller the field of view. Looks like you guys get this, but we'll just do one more quick example. So low power. My eyepiece power is 10x. What's the objective power? The objective lens, 4x, for a total magnification of? What would my field of view be? Small, medium, or large? A large field of view. So if I were looking at some hideous creature under the microscope, it might look something like that.
Oh, I get it.
Oh, it is?
I was about to say that.
I thought it was a different picture. All right. If I then switch to medium power, what would my eyepiece power be? And the objective? And the total magnification? Giving me a total magnification 100 and a field of view? Medium? If you don't like gross things, you might want to look away from this picture. You don't have a queasy stomach. All right, and then finally, if I zoom in on this bizarre, strange beast, under high power, what's my objective lens power?
40x.
40x. For a total of?
400.
What kind of field of view?
Small.
Okay. Brace yourselves.
Like actually, gross.
That's not even him. That's his eyes.
Yeah.
No, it's
No, it's
He doesn't shower that much, so sometimes you get these eye infections. All right. What?
That doesn't make sense.
What, if you don't shower to get an eye infection?
You don't wash your eyes.
He's got all that grime on his face and just washes in his eyes. Anyway, enough about Mr.
Anyway.
So, this is our field of view, the area we see. Now, when we are looking at things in the microscope, they're usually pretty small. So we have a special unit that we use. We're not going to measure things generally in meters or centimeters. What we see is pretty small. Even millimeters are very small. And so sometimes we switch to a different unit. The unit is called micrometers. The symbol for it is this Greek letter. It looks like a cursive U. That's the symbol for like micro. So this is micrometers, micrometers. And there are 1,000 micrometers in 1 millimeter. So if you take those tiny little millimeter markings on a metric ruler, if you were to divide it into micrometers, you'd have to draw 1,000 of them. So a micrometer is very small.
How do
You put it. And so to convert from one to the other, if something is 3 millimeters wide, how many micrometers?
3,000.
3,000. If something is 6,000 micrometers wide, 6 millimeters. Okay, so we could convert back and forth by multiplying by 1,000 or dividing by 1,000. By moving a decimal place to the right 3 spots or to the left 3 spots.
It looks like a upside down face.
So look at this ruler. It's showing you 6 millimeters of width in the field of view. So how many micrometers is that field of view?
6,000.
All right. If I were to look at some graph paper here, that each one was a millimeter apart, what's the diameter of this circle? 5 millimeters or 5,000 micrometers. What about this one? How many millimeters do I see here? 1?
I know.
Not 1.
1,000 or 1.
How many millimeters?
Oh, 1.2.
All right, 1, and then there's some space on each side.
How do you tell?
You estimate.
You can't fit a
So
square.
it's more than 1, right? So you kind of say, all right, about 0.2. How many micrometers? Good. Move the decimal place and 3 to the right. All right. Last thing for us to talk about before we can move on to actually using a microscope. Estimating the size of specimens is something you'll have to do. So, we have Mr. Arcuri standing next to the tree. So if you know this tree is 6 meters tall, how tall is Mr. Arcuri?
2 feet.
2 feet?
2 meters.
2 meters? Why are you
That
saying
is
2
not-
meters?
2 meters is like 5 meters.
Jack?
I would say 2.5.
Because you are 1/3 the size of the tree.
So you sort of estimate, like how much compared to the tree, how big is Mr. Arcuri?
5 feet tall.
So we estimate, yeah, maybe 3 of him, if you stack 3 of him on top of each other, made a little Arcuri pyramid or something. That means 1/3 of the tree size is the size of Mr. Arcuri. And so how that is 2 meters.
I thought that thing in the left microscope was Mr. Arcuri.
I do see the similarity. All right, so we could do the same procedure using a microscope. If I'm telling you the field of view is 10 millimeters, how big is this creature?
4 or 5 millimeters.
You gotta, it's an estimate. It's not going to be exact. Maybe it takes up about half of the space. Maybe you could fit 2 of them across. So therefore, 10 divided by 2 is 5 millimeters. How many micrometers? 5,000. How big is this green creature?
1 millimeter.
Yeah, I'd say a millimeter. About 4 could fit across. 4 divided by 4 is 1 millimeter. Or 1,000 micrometers. Whoa.
Cookie Monster.
How big is this?
8 millimeters.
Or
8,000.
this?
Oh, is that?
No.
6.
This is 6 millimeters, this creature?
It says 6.
That's the field of view.
3.
Yo, did you get that from
You could
class,
fit 3 across.
Did you get that from class, though, Joe?
6 divided by 2.
Oh, that makes sense.
How about this?
3.
Yeah, 3. Could fit 1 on this side, 1 on this side, I think.
No, that's from cooking.
How big is Cookie Monster?
5 feet tall. 5 or 4.
5 millimeters.
9 feet tall.
All right.
Our own is 17 feet tall.
That could be. I do see.
Yeah, it's like 17.
All right, any questions about anything related to microscopes?
How is Cookie Monster that small?
All right, we're going to get to use them now.
Cells and